So much for the introduction and for the opportunity to be here. It really is an honor to be spending part of the afternoon with all of you and also to be alongside such great colleagues to share this presentation. So again, my name is Drew Gronewold. I'm an associate professor at the University of Michigan in the School for Environment and Sustainability. And today my talk is going to be broken up into 4 brief parts. First, I want to give you a little bit of background and context for what it means from a hydrological process and even a climate perspective to try to understand water level variability on the Great Lakes, and not just to monitor it, but to represent water levels in long-term forecasting models. It's a major challenge. Second, I want to take a snapshot look at historical water levels, so we're all aware of what the historical water level record entails and what we might be able to learn from it. And then I want to dive a little bit into our understanding of what makes water levels go up and down through our understanding of the water balance. And then I'll finish off with just a few brief perspectives on long-term water level forecasts. But before I go any further, I do need to make sure I thank some sponsors and some individuals. First off, the team that I have here at the University of Michigan, just a wonderful group of postdoctorate fellows in the top row there, graduate students in the middle row, and then we're very fortunate to have talented undergraduates here as well on our team. All of them, without their help and their contribution, really none of the data and the slides that I'm showing would have been possible. I also want to thank a lot of my former colleagues at NOAA, at the National Oceanic Atmospheric Administration, in particular those based in the Great Lakes Environmental Research Laboratory, as well as the partnership through the Cooperative Institute for Great Lakes Research. Really just an amazing group of scientists that have been providing foundational science on the Great Lakes for roughly 40 to 50 years. So I want to pay tribute to those colleagues as well. And then finally, the sponsors for a lot of the research that you're going to be seeing for the past several years include NOAA, the Army Corps of Engineers, United States Geological Survey, the Great Lakes Protection Fund, as well as the Council for Great Lakes Governors and Premiers, and the Michigan Department of Transportation. So let's start off with a little bit of background on tackling the Great Lakes. And I think this satellite image of the Great Lakes sort of underscores the challenges we face when we try to understand all the different forces at play that are driving water levels over short-term timescales on the order of hours, days, and weeks, all the way out to months, years, and even decades. So this satellite image, you can see the outline here of Lake Superior. You can see the western shoreline of Lake Michigan here, Green Bay, the lower mid of Michigan down here to Lake Erie and off to Lake Ontario. 2 sort of take-home messages from this slide, aside from just the magnitude and the scale of the processes. One is that the lakes are huge. They represent a prominent force on the landscape. But I also want to mention that we cannot learn about the lakes or about water levels purely by monitoring the land surface alone. Most hydrologic and climate science, at least when it comes to terrestrial processes, is focused on understanding rainfall and evapotranspiration, processes that take place on the land surface. One of the challenges we face with the Great Lakes is that we have to take measurements and run models out over the surfaces of lakes that really behave almost more like oceans than moderate-sized lakes. And you can see that in this image where we have processes out over the middle of the lakes that are noticeably different from what's happening over the land surface. So a brief point of context there in terms of the scope of the problem we're trying to address. This image brings things a little bit more close to home in terms of the Great Lakes and the basin. So the tan area is the boundary of the Great Lakes Basin. And what you can see here is that the Great Lakes themselves take up roughly 30 to 40% of the entire area of the basin, just an extraordinary extent of lake water surface. And just for reference here, when we look at the Great Lakes from a flow perspective, we know that water, collects in Lake Superior, flows down through the St. Mary's River into Lake Huron, interchanges with Lake Michigan through the Straits of Mackinac, and continues flowing down through the St. Clair River and Detroit River, through Lake Erie, over Niagara Falls, out through Lake Ontario, and out through the St. Lawrence River. A couple of the highlights here, you see there are some diversions of water into and out of the Great Lakes. Here we have diversions of water into the Great Lakes Basin at the Agokie and Long Lake diversion. And although it's not labeled clearly, there's also a large diversion of water out of the Great Lakes here at Chicago, which many of you know of. So this is just simply a reference map to get us oriented to the overall system. So let's go next and let's take a look at water levels on the Great Lakes. Later on, you're going to be hearing some wonderful talks about short-term and mid-range processes Today, I want to emphasize water level changes on more of a monthly, seasonal, and even a multi-decadal scale. We're very lucky on the Great Lakes to have water level measurements that go all the way back to 1860. So on this slide, we're actually going to look at a composite of all the water level records on each of the lakes. On the bottom axis here, you can see water levels going back to 1860, all the way up to just a few months ago. On the vertical axis here, we can see water level surface elevation in meters. So what I want to point out here is that these scales are comparable to one another. So for example, when we look at the water level data here for Lake Superior, the scale of the numbers here is the same as the scale that we're looking at for Lake Michigan, Huron, and Erie. There's just a big gap here to represent the change in elevation as water goes through the St. Mary's River. And similarly, there's a gap here in the elevation, primarily due to the drop of water over Niagara Falls. But we're comparing apples to apples and oranges to oranges when we look at the range of variability. So within each one of these data sets, we have three different types of points here. We have dark blue dots that represent the annual water level on each one of the lakes. We have light blue dots that represent the monthly average water level. And then we have a red line that represents the long-term average. One thing I want to point out is that with long-term water level records like this one, where we're averaging water levels over years and months, we view Lake Michigan and Huron as one large lake. And that's in part because the Straits of Mackinac are relatively deep and wide, such that the average water level over the entire surface of both lakes tend to be about the same when we average it over these long time periods. And that's why you see Lake Michigan and Huron combined into one data record in this particular plot. Now, we could spend an awful lot of time looking at all the ups and downs of water levels on this plot, but I want to highlight just a few time periods and geographic domains to emphasize when we look at this record. One of which is if you look at the outlet, if you look at Lake Ontario, starting in around 1960, many of you know that the outflow from Lake Ontario began to be regulated in the mid-1960s when the Moses-Saunders Dam was constructed. And one of the things you'll notice is if you look at variability from year to year across the entire system, you can actually, there's a visually identifiable reduction in the variability due to the construction of that dam on Lake Ontario. And this brings up a range of issues regarding what constitutes natural variability across Great Lakes shorelines and what constitutes anthropogenic control across the Great Lakes. Many people view that control of water levels on Lake Ontario as an ecological disaster because it diminished the areal extent of a lot of the natural wetlands on Lake Ontario. But it's an interesting point to look at nonetheless. Now, if we shift and look across all the upper lakes from, let's say, the late 1990s until about 2010, we enter what many people remember as a period of pronounced low water levels, particularly on Lake Michigan, Lake Huron. In fact, in January of 2013, Lake Michigan and Lake Huron hit their all-time record low water levels. And this prompted a lot of people in the media and the public domains to ask questions about where that water was going. This particular image appeared in the news that shows Lake Michigan on the left. And instead of Lake Huron on the right, we just see a large drain, sort of evoking this image that we have really no idea where the water has been going, but it's going and is going fast. And a lot of the narrative around water levels during that time period was influenced by, from my perspective, a national narrative related justifiably to climate change, but also to a narrative that evolved around aridity and drought. So the idea that temperatures are going up, evaporation is going up, this is happening all around the country, and the Great Lakes are potentially falling into that paradigm. But if you just wait a few years, what happens here on the Great Lakes is that things can change. And so starting in 2014, this last time period that I'm highlighting here across all the lakes represented the fastest rate of water level increase ever in recorded history. So put differently, on Lake Superior and Lake Michigan and Huron, between 2014 and 2019, water levels had never risen as quickly over that same number of years. Just an extraordinary turnaround in water levels. This led to record highs on Lake Erie. Monthly records were set on Lake Michigan. And here's a point I want to make to everybody that I think is absolutely profound. Lake Ontario is regulated. It's designed to have a constraint on the highs and lows. But so much water came through the system in 2017 and 2019 that if you look at the bottom right here, you can see these two light blue dots. In 2017, and then again in 2019, all-time record highs were set on Lake Ontario, and they happened during this period of regulation. So from our perspective in hydrology, we attribute that to an extraordinary amount of water that came through the system, and it simply couldn't be controlled. I'll talk more about that in a minute. But during this time period when water levels surged, there was a lot of attention again on what might happen when water levels are high and how we mitigate high water levels. This is an image that came from a cover article we wrote for the journal EOS, but it's sort of, I like this picture because it's sort of an iconic image of the Chicago skyline as well as the bike path here flooding in 2015. I found it also interesting that the Chicago Tribune ran a cover article in February of 2021 around this time period that water levels were extraordinarily high, indicating that the city of Joliet, just outside of Chicago, was running out of water. And this is an important narrative regarding the Great Lakes water level story, that even when there are periods of water level abundance on the Great Lakes, there are areas along the periphery of the Great Lakes, particularly those that draw from groundwater aquifers, that either have contaminated groundwater or the groundwater aquifers are literally running dry as they did it in Joliet. So it's an amazing sort of contrast and juxtaposition we have here in the Great Lakes, where the Great Lakes Compact prohibits the transport of water across the Great Lakes Basin. There are periods when we have water abundance in the Great Lakes, yet there are communities outside of the Great Lakes that are literally running out of water. And this is something that we're paying a lot of attention to in our research. So what I want to do next is shift gears and talk a little bit about both conventional as well as new understandings we have about the water balance of the Great Lakes. Essentially, what that means is the amount of water coming in, the amount of water leaving, and any change in that being reflected in water levels, and what we think might be happening in the future. So just to make sure we start off on the same page, this graph that I'm showing on the screen on the left-hand side shows a basic summary of the key components of the Great Lakes water balance. So what I have here is for each of the lakes, we're summarizing the total amount of water that comes into each lake and leaves each lake through these three main, what I call water balance components. And the first, represented by the green bar on each lake, is runoff. That represents all the water that comes into each lake through rivers and streams, but not through what we call the major connecting channel. So I'll refer to that in a minute. But for example, the St. Mary's River is not included in these totals. Lake Superior does not have a major inflowing river coming into it from an upstream lake. So we have here in green all the water coming in through rivers and streams. This blue bar represents the magnitude of water that comes into Lake Superior directly from precipitation on the surface of the lake. And I want to pause here for a moment and just underscore how extraordinary it is that Lake Superior and Lake Michigan and Lake Huron receive more water through rainfall and snowfall on the surface of the lakes than they do for the water that hits land and comes in through rivers and streams. It's really hard to find any freshwater system on Earth that has that same characteristic. Finally, the pink bars that you see in each one of these panels represent the amount of water lost through evaporation off the surface of the lakes. The numbers that you see at the top or the bottom of each one of these bars represent a long-term average flow rate. We convert these numbers into flow, as you'll see in a minute, for comparison to the channel flows, but these are in thousands of cubic meters per second. So this represents just the amount of water coming into and leaving each lake basin through these major components. Now, if I shift gears and look on the right-hand side of the screen, we can look at the magnitude of water that transfers in between each one of the lakes. So for example, this green bar right here that I'm highlighting with the 2.2 above it, that is the flow out of Lake Superior through the St. Mary's River into Lake Huron. And on long-term average, it has a flow of around 2,200 cubic meters per second. As we go down through the system, through the St. Clair and Detroit River, and then out through the St. Lawrence Seaway, we can see that flow increasing. By the time water leaves Lake Ontario, on average, it has a flow of around 7,000 cubic meters per second. And I just want to pause and highlight that for a moment. 7,000 cubic meters per second is an awful lot of water. It's really a continental scale flow. If you look at flow in other rivers around the continent, it turns out that the flow through the St. Lawrence Seaway, by the time it reaches the Gulf of St. Lawrence, is the second highest continental discharge off of North America. Mississippi River is number 1, St. Lawrence is number 2. And all these other rivers, the Yukon, the Columbia, they fall well below the discharge from the St. Lawrence Seaway. So these are major flows that we're talking about here. And then finally, these flows right here, I mentioned earlier the diversions into and out of the Great Lakes Basin. This pink bar represents the amount of flow coming into the Great Lakes through the Agoki and Long Lake diversion. And then this bar represents the magnitude and the approximate amount of flow that leaves the Great Lakes through the Chicago diversion into the Sanitary and Shipping Canal. So we take a look back. What you see on the screen here is really a summary of the major inflows and outflows through the Great Lakes system, and seasonal and long-term changes in these amounts are what ultimately change water levels on the Great Lakes. Now, there's been a lot of research done to understand different hydrological processes. One of the areas of research that I'm most excited about over the past decade has been understanding evaporation. So if you remember, I mentioned earlier about to understand Great Lakes water levels, you have to get out over the lakes. Some of you who have been with me on a talk like this before have heard me say this, but this is a lighthouse. Many of you might recognize the White Shoal Lighthouse on the northern end of Lake Michigan. It still is active as a passive Coast Guard station, but it turns out it's an ideal location for an evaporation tower. And so when I was at NOAA, we partnered with several colleagues, including Peter Blanken of the University of Colorado Boulder, who ultimately worked to install 6 evaporation towers on lighthouses like this one across the Great Lakes. We look at this image and we think it would be a great opportunity for a student winter internship program, although that would probably violate some OSHA regulations. But nonetheless, this is an example of how the Great Lakes community has been learning more about the water balance components and what drives water level change. I also want to show you a result from a paper that we published recently. My colleague, Eric Anderson, was the lead author. What you're seeing here is an image collected from what we call a thermistor chain that has been deployed at the bottom of Lake Michigan for decades. A thermistor chain is a long string of connected, basically thermometers that are measuring long-term temperature in the Great Lakes. It's moored or it's anchored on the bottom, and then it leads upwards and it's held just below the surface. So it measures depth, it measures temperature at various depths throughout Lake Michigan. And what we did is we looked at the results of decades of temperature measurements from this thermistor chain, and we integrated them into long-term trends in each month of the year and at various depths. So in this particular image, what you're seeing is in each one of these square or rectangular cells, you're seeing a color that reflects the long-term trend, either in terms of warming or cooling in a particular month and at a particular depth. And what we found that was somewhat astonishing was when we looked at this long-term record, we found that in the months of January, February, March, and April, down below the surface, which is where we typically get our understanding of the Great Lakes, we're seeing this extraordinary pocket of warming happening in the winter, which led us to sort of put together the phrase that winter is vanishing from one of Earth's largest lakes. What we also see that's interesting, though, is other areas where there's a cooling. So there's a shift in the balance of the heat content of the lakes, and this has major implications for long-term ice cover as well as evaporation. And this ultimately made its way into the journal Nature Communications with this title right here. I also want to share with you some research that we've been doing that take a look at just exactly what's been happening in terms of the water balance that's led to these major swings in water levels over the past several decades. So this slide has an awful lot of information on it, but what you're seeing here are different components of the water balance over time, starting back in 1950. So each panel is a time series, starting in 1950 and going through relatively roughly to the present. Each one of the panels has a water balance component shown. So in the upper left-hand corner here, we're looking at precipitation on the land. And then this next panel in the top middle is evapotranspiration from the land. And then the upper right is essentially the difference between the two, which is more or less what we get in terms of runoff. The bars have different colors to represent either positive or negative anomalies. In other words, how far above or below the average were each one of these water balance components over time. And the black line represents a long-term sort of trend or a smoothed average line. So for example, if we look at precipitation on the land surface of the Great Lakes, we can see not only that precipitation has been going up relatively steadily, But the gray area that I highlight, sort of the past decade or so, was pretty extraordinary when it comes to back-to-back years of precipitation. But what's interesting is that on the land surface, we also see a consistent increase in evapotranspiration, the amount of water that's lost primarily through plants. And this is consistent with what we get when we read the literature on climate change, that increasing temperatures are going to allow the atmosphere to carry more moisture and bring more precipitation to the Great Lakes, but they're also going to lead to increased evapotranspiration on the land surface. What we found fascinating is when you look at the lakes themselves, not just the land surface, but the surfaces of each lakes, we can start here on the bottom left, and this is an image of what we are seeing over the surface of the lakes through an extraordinary surge in precipitation on the surface of the lakes over the past decade. And then here's another part that we found fascinating. When we looked at the evaporation record over the surface of the lakes, many people assumed that evaporation on the surface of the lakes would continue to be going up. In 2014, many of you remember there was an Arctic polar vortex deformation. Some people refer to it as to the polar vortex in the media. The lakes got very cold and evaporation slowed down. So to finish off this slide, what I want to show you is if you have the Great Lakes and we have a water balance based on precipitation coming in and evaporation leaving, and for a period of about 10 years, precipitation goes up and through the roof and water lost through evaporation slows down, we have on the bottom right here the net amount of water coming onto each of the lakes. And it was that net amount of water that really drove that ultimate surge in water levels that we saw over the past decade that led to those record highs. This phenomenon in which we have precipitation increasing and gaining strength over time through climate change, but also evaporation tending to go up, but with a lot more variability, we're referring to this almost as a tug of war on the long-term water balance of the Great Lakes. And we summarize those ideas in a recent paper in Geophysical Research Letters. So I want to finish up with just a couple comments here about long-term water level projections. So if you want to run a model that simulates water levels of the Great Lakes, looking out years or even decades, you not only have to simulate precipitation, evaporation, and runoff, but you also have to simulate continental movement of air masses that influence what precipitation and evaporation are going to be in the Great Lakes. And this image sort of summarizes what those major air masses are. So for example, in the bottom right, one of the common air masses that influences North America is this maritime tropical air mass, warm, moist air that sometimes comes out of the Gulf of Mexico. When that air mass dominates our system, we have an increase in precipitation and things get warmer. But we can periodically have continental polar air from the upper middle part come into the Great Lakes, and that's very dry and cold. What I want to point out is that forecasting the long-term behavior of these air masses is incredibly challenging, yet it's something we need to do if we're going to understand how water levels are going to change over the coming years and decades. And finally, I'll leave you with this slide right here, which has to do what I think is a sort of a trade-off between long-term water level projections and management decisions. This is a quote from a water manager from the New York City water distribution system, who basically was quoted as saying, 2100 doesn't keep me up at night, indicating that even though there may be a long-term trend in water supply or water levels over multi-decadal periods, their management decisions that need to be made on much shorter timescales, and the variability we expect to see in Great Lakes water levels over the coming months and years is likely to match and even surpass the variability that we've seen in the past over those shorter term timescales. So I will leave it at that. And I believe we have a few minutes for some questions before we transition to the next speaker. So thank you.